I'm Dr. Roger, and today we're looking at second-order linear homogeneous ordinary differential equations with constant coefficients. The general second-order linear takes this form. If the term on the right-hand side with just the variable is 0, this equation is called homogeneous. And if P, Q, and R are constants, then we refer to it as second-order linear homogeneous ordinary differential equation with constant coefficients. I've already solved this with a 3 and a 4 here in other videos. I'm going to do it with a 5. The approach to these constant coefficient problems is, if it's homogeneous linear ordinary differential equation with constant coefficients, we assume y equals e to the rt, and I will justify that later. That gives us y prime for r equals constant is r e to the rt, and y double prime equals r squared e to the rt. So y double prime becomes r squared e to the rt, and 4y prime is 4r e to the rt, and 5y is 5 e to the rt, and all that equals 0. Factoring out the common factor of e to the rt, e to the rt times the quadratic r squared plus 4r plus 5 equals 0. Since the exponential is never 0, we know the quadratic is 0, and we can solve for the zeros of a quadratic, in this case with the quadratic formula. R equals negative b plus or minus root b squared minus 4ac all over 2a, where a equals 1, b equals 4, c equals 5. And I'll always write down my quadratic formula when I'm doing differential equations to avoid careless errors. So r equals negative 4 plus or minus square root 4 squared is 16, minus 4 times 1 times 5 is minus 20, 2a is 2. So r is negative 4 over 2 is negative 2, plus or minus 16 minus 20 is negative 4, square root of negative 4 is 4i over 2, so that's negative 2 plus or minus 2i. Our solutions are y equals e to the rt. I'm just going to take the plus solution, so y equals e to the negative 2 plus 2i t. And this is not very useful in this form, so I'm going to rewrite it using Euler's formula. Recall, e to the mu t equals cosine, e to the I mu t equals cosine mu t plus I sine mu t. This is Euler's formula. And you can just justify this with power series, but I won't do that today. So e to the negative 2t plus 2it is e to the negative 2t times e to the 2it, which is e to the negative 2t times cosine 2t plus I sine 2t, where the negative 2 in the exponent comes from here, and the 2t and the cosine and the sine come from the imaginary part. I unfortunately chose an example where the real and imaginary parts have the same absolute value. So this gives me a solution y equals e to the negative 2t cosine 2t plus I e to the negative 2t sine 2t. And we have a theorem that says if y equals u of t plus I v of t is the solution to a second-order linear homogeneous ordinary differential equation, whether it's constant coefficient or functional coefficients, then if the coefficients are real, which these are, u of t and v of t are solutions. So if p of t, q of t, and r of t are real value, then u of t and v of t are solutions. So in this case, we have two linearly independent solutions, y equals e to the negative 2t cosine 2t, and let's call these y1, y2. y2 equals e to the negative 2t sine 2t. So our general solution is y equals c1 y1 plus c2 y2 is c1 e to the negative 2t cosine 2t plus c2 e to the negative 2t sine 2t. If I wanted to prove that those are solutions, which is worth doing but takes more time than I want to put into this video, I could take y1 prime and y1 double prime, substitute them in here, and I would find out that it is in fact a solution. And the same for y2, y2 prime, y2 double prime. To show that they're linearly independent, I can take the Wronskian, and I will do that. The Wronskian of y1, y2 equals the determinant e to the negative 2t cosine 2t, and this is going to be ugly, negative 2 e to the negative 2t cosine minus 2 e to the negative 2t sine. I guess I have to erase some of this. My second column is e to the negative 2t sine 2t and negative 2 e to the negative 2t sine 2t plus 2 e to the negative 2t cosine 2t. That determinant is this product, which is negative 2 e to the negative 4t sine 2t cosine 2t, and then plus 2 e to the negative 4t cosine squared t, cosine squared 2t. And then minus this product, so minus the negatives, plus 2 e to the negative 4t times sine 2t cosine 2t, and then minus the negatives plus 2 e to the negative 4t sine squared 2t. These two terms cancel, so I'm left with 2 e to the negative 4t, factoring that out, cosine squared plus sine squared of 2t. And the Pythagorean identity tells you the parentheses are just 1, so my Wronskian of y1, y2 is 2 e to the negative 4t, and that exponential is never 0. Since the Wronskian is non-zero, our two solutions are linearly independent. If you substitute them in, you verify that they are in fact solutions, and therefore, based on our theorems for existence, uniqueness, superposition, etc., all solutions can be written as a linear combination c1y1 plus c2y2 for these functions. Remember that if your characteristic polynomial has roots lambda plus or minus mu times I, your solutions are y1 equals e to the lambda t cosine mu t, and y2 equals e to the lambda t sine mu t. And this is a shortcut that saves the algebra and power series approach to deriving those solutions. Come back soon for my next video. With math, there's always more.